Hi, people. It's Mrs. Garber again, and I'm glad to see you. This is now part 3. Right, in part 3, we're going to look at the aldehydes. That's part of the formal group. The aldehydes and then the ketones. So the functional group of the aldehydes is where we get a double bond of oxygen at the carbon atom. So the functional group of the aldehydes is also always at the end of the chain. So the suffix then being Al. So the functional group, as we just said, is a double bond oxygen and an H then at the carbon atom. And it will always have the suffix of L. So if you look at this example here, where we have 3 carbons, it is then prop, and because of the single bonds, it's an ane. The E is then replaced with propanol. So it's propanol. That is then the IUPAC name of the 3 carbons of the aldehyde. The general formula here also being CnH2nO. So you do not need to count the number of atoms here. Why? Because the functional group will always be at the end, at the terminal site. So that will always be at the first carbon. Therefore, you don't need to count the numbers. Right, now when we look at the example here, where we've got in 1 carbon, it's meth, and then the suffix is al, so it's methanol. And applying a general formula, the molecular structure is then C for 1 carbon, H2O, CH2O. Here we've got 2 carbon atoms, so it is then ethanol. Like we said, the functional side is always at the end of the carbon chain, and so it's C2H4O. And recall here again, you can see there's a difference of 2 hydrogen atoms from the first to the second carbon. Therefore, it also forms a homologous series. Right. Functional group then of the ketones. So we've just done the aldehydes, where you've got a double bond and a double bond oxygen on the carbon with an H at the end of the carbon chain. Here you have it between 2 carbons. Here you've got a double bond oxygen on the carbon between 2 carbons. That is the functional group of a ketone. That's part of the carbonyl group. So the suffix then being -one. So if you look at the 3 carbons here, right, it is then prop, and it is at the second carbon. So it's 2-propanone. The suffix then being -one. So you can also write it as propan 2-one. In this example, we didn't need to count or number the carbon atoms because there is only 3. You cannot get a ketone with less than 3 carbons because it has to be, the carbon has to be between 2 carbon atoms. So this is your basic example, your most simplest example of a ketone. And therefore you don't need to number it because whichever way, 1, 2, 3 or 1, 2, 3, it will be at number 2. So the general formula here then also being the same as the aldehyde, CnH2nO. Right, so another example here, we've got 4 carbons. You have to then number your carbon atoms from your functional side first, being the left side here. So it is then the double bond oxygen is then at your second carbon, being 4 carbons. It is but or but, like most people say but. So it's butane. The E is then replaced by the -one. So you can write it 2-butanone or butane 2-one. Right, the molecular formula here then being C4H8O, where you've got an extra carbon, 5 carbons. You'll see that the molecular formula also differs with 2 hydrogens. With 5 carbons in comparison with 4 carbons, there is 2 hydrogens added. So it's also a part of a homologous series. So here we see the functional group is at the right-hand side of the carbon chain. So you number your carbon atoms then from the right-hand side, and then the functional double oxygen being at carbon 2, 5 carbons then, it's pent. So it's pentan 2-one or 2-pentanone. Right, pentan 2-one or 2-pentanone. That is then your IUPAC name. Right, so you can see the difference then of the aldehyde with the ketone. I'm comparing it here. The aldehyde, the functional group, always being at the end of the chain, and the ketone always being between 2 carbons. So if you compare the aldehyde and the ketone, you note that the molecular structure is the same. Yeah, if you count the C carbons, it's H6O, deriving from the general formula. So your general formula and your molecular formula, your molecular structure is the same. It's also here, C3H6O, your molecular formula, derived from your general formula. So in your aldehydes and your ketones, you've got the same molecular structure and the same general formula. So that is exactly the same. But now, where does it differ? We just looked at the difference. So the aldehydes and the ketones differ in their functional structure. And because of that, they are called isomers of each other. So we know by definition an isomer is where you have the same molecular structure but different functional structures, where the aldehydes and ketones are very good examples. Molecular structures being the same, functional structures being different, the general formulae being the same. So here we have 1, 2, 3, 4, 5. That's then pentanal. Okay, remember the alcohol is ol and the aldehydes are L. The suffix is L. So it's pentanal. The ketone, where the suffix is -one, and specifically here, it can be from left to right or right to left. The double bond oxygen will be on carbon number 3. So it's pentan 3-one or 3-pentanone. So here's a very good example of isomers. We have the same molecular structures, the same general formula, but the functional groups being different. With the aldehydes, the functional group is always at the terminal side of the carbon chain, terminal being the end, and the ketones, the double bond oxygen must be between 2 carbon atoms. So you'll never get a ketone. You can't get a ketone where there's not 3 or more carbon atoms. Right, so I do hope that you have now a better understanding of these functional groups that we have done up to part 3. And I made a summary then also here of the general formula of the alkanes. If you can still recall, CnH2n plus 2. The alkenes just been CnH2n. Alkynes CnH2n minus 2. Haloalkynes CnH2n plus 1x. Alcohols CnH2n plus 1OH. The aldehydes CnH2nO. The ketones CnH2nO. So now I'm looking forward to explain to you the carboxylic acids and the esters. And then we can really do some nice exercises and really start looking at the compounds with all the stuff, as many branch groups that we can possibly get, and look at some of the examples that you find in tests and in exams. Thank you, people, and I really hope I could contribute to you understanding and having a good summary of the functional groups in organic chemistry.